Welcome back, everyone. We are starting chapter 6 today. And chapter 6 is our normal probability distribution. This is a big one. This is the beginning of us getting ready for chapter 8, which I keep mentioning is a really big one. So let's dive into it. So we are going to be talking about, as I mentioned, a normal probability distribution. And we're going to start with a uniform probability distribution, which is a little boring, but it kind of gets the point across. So a probability density function, PDF, by the way, that PDF has nothing to do with like a file, PDF files or anything like that, different PDF. A PDF is an equation used to compute the probabilities of continuous random variables. Chapter 5 was about a discrete random variable. We are now to a continuous random variable. It must satisfy two properties. The total area under the graph of the equation over all possible values of the random variable must exactly equal 1, meaning 100%. The height of the graph of the equation must be greater than or equal to 0 for all possible values, meaning the area is always above the x-axis or z-axis or whatever axis we're calling it. So this is a good example here. You have a friend that's always late. Let x represent the number of minutes late. And suppose that all times between 0 and 30 minutes late are equally likely. This is a uniform density. And making x equals 0 is they got there on time. So if we're on the x-axis going from 0 to 30, then the height must be 1 over 30, because when we multiply 30 times 1 over 30, we get exactly 1. So here's our first distribution. And excuse me, I have a bit of a cough. We're now going to view area as a probability. This is a big deal. Stop it. Area as a probability, meaning area under the curve represents a probability. And the x-axis is going to be whatever we label. In this case, it's minutes late for my friend. And there's two things we're going to be looking at. Given information on the axis, what is the area? Or we're given the area and we want to find some information on the axis. So those are going to be the two main things that we're going to be looking at. So what is the probability your friend will be between 10 and 20 minutes late? Well, this right here represents 10 minutes. From 10 minutes late to 20 minutes late, that's a total of 10 minutes. And the height, again, is 1 over 30. So base times height, or length times width, however you want to view it. That's a 3. 30. It's going to give me 1/3, which is about 0.3333. So about a 33 1/3% chance that my friend will be between 10 and 20 minutes late. Then we're going to go the other way. You're going to meet your friend at 10 o'clock. You arrive on time. There's a 20% probability your friend will arrive in the next how many minutes? So now we're given the area. And this is hard to see down here. Let me make that a little bit bigger. This variable here is x with a little 0 down there. Pronounce that x naught. That's spelled N-A-U-G-H-T. And the area, in this case, is given as 0.2. We know the height is 1 over 30. We just don't know how many minutes my friend is going to be late. I now have an equation. I'm going to solve for x naught. I'm going to multiply both sides by 30. This means x naught is equal to 0.2 times 30. So my friend, there's a 20% chance that my friend will be 6 minutes late. Not too bad when it's uniform like that, when we have nice pretty rectangles. Of course, in real life, when we have a normal distribution like we have here, rectangles aren't going to cut it. So we're going to have to use some technology here. Properties of a normal density curve. It is symmetric about the mean mu, which we can see is right in the middle here. The total area under the curve is exactly equal to 1. Now, I want to be clear. The blue, as it gets closer and closer to the x-axis, is actually going off to infinity in the x direction and in the negative infinity in the other x direction. The graph approaches but never touches the x-axis, and there's a correspondence between the area under the curve and the probability. Now, we've seen this before. This is the empirical rule, and today we'll be able to actually calculate this out. Now, what we are trying to do now is visualize if we go one standard deviation out and we get this area here, all the way to the edges here, that area is going to translate to be exactly 68%. Meaning if I am here, from here to here, it's going to represent 68% of all of that probability, all that area of the curve. If we go 2 standard deviations out, meaning 2 up and 2 down, then we are going to go a total of 95%. And if we go 3, which we rarely do, that'll be 97%. You can see the little tiny area that's left down here, not very much there. Not very much there. So let's put this into practice here. Suppose that a monthly charge for cell phone plans is normally distributed with a mean, meaning an average price is $58, and the standard deviation is $15. We're going to draw the normal curve with the parameters labeled. So we're going to start here. We're going to start with, right in the middle is going to be 58. Let's change color a little bit. 58. This represents money, is this x-axis, as it were. So this is in dollars here. Now, because we are going by standard deviations, which in this case, the standard deviation is 15, we can see over here. Here's the 15. So I'm going to take the 58, and I'm going to add 15 to that. 15 from there. 15 plus 58 is 73, plus another 15, 88, plus another 15. We'll go 3 standard deviations out at $103. Now we're going to go the other way. 58 minus 15, 43, minus 15, it's 28, minus 15, down to 13. Now, $13 seems really cheap for a cell phone plan, but look how rare that is. A very, very low probability of that. Second part says shade the region that represents the proportion of plans that charge less than $43. Okay. So here's 43, and we're going to shade in the region that represents less than 43. So that's all this region here. So all that area represent all the plans that cost less than $43. And they're going to tell us what that area is. For part 3, it says, suppose the area under the normal curve to the left of $43 is 0.1587. By the end of this lesson, we will know how to find that value. Provide 2 interpretations of this result. I'm going to actually provide 3 interpretations of this result. One of them is the proportion of cell phone plans less than $43 is 0.1587. Another explanation would be the probability that a randomly selected cell phone plan is less than $43 is 0.1587. And the last way I'm going to interpret this is I'm going to say let me word it this way. 15.87% of the plans are less than $43. I like that one best. That one, I think we all understand percents. All right. We have another one here about refrigerators. Refrigerators, the lives of refrigerators are normally distributed with a mean of 14 years and standard deviation of 2.5. We're going to start out by writing in the labels here. So this is going to be in years now. And right in the middle, we have 14. Standard deviation is 2.5, so 14 plus 2.5. 2.5 plus 2.5. Going the other way now, 14 minus 2.5 minus 2.5 minus 2.5. All right. It now says shade in the region. That represents the proportion of refrigerators that last more than 17 years. I'm going to go right here. That's going to be here that wants more than 17 years. There we are. And they're telling us that this area under the curve is 0.1151. That's the third part there. And provide an interpretation. I will. So about 11.51% refrigerator, I'm sure I'm misspelling that. There's no D. Refrigerators last more than 17 years. All right. Standardizing a normal random variable. Now, I want to point out we have seen this formula before with a z-score. That's not new. What that does is this makes the z value is going to be the number of standard deviations away from the mean, and the mean is going to be 0 with a standard deviation of 1. That keeps it nice and simple and standardized. All right. So what we're going to do for this first example is we're going to find the probability using the normal distribution. We're going to have to use the calculator for this. So get your calculators ready. And they want to know the area of the curve when z is bigger than negative 0.69. So I'm going to actually draw a picture here. Now, we're doing standard normal now. This is now a z. Now, we need to understand that the negative numbers are to the left of 0 and the positive numbers are to the right of 0. And what we're going to do is we are going to shade in the area. So here we have our negative 0.69, and they want to know when it's bigger than that. And we are going to be using this function in our calculator. Now, this is the way that it gets written out for a TI-83 or 84, or even my free one that I have here. It's going to be this way. If you have a Casio, then the mean and standard deviation switch. Here's how we dig this out. We're going to have to hit second and then distribution. It's the same we did with the binomial distribution. So second, and then above the vars button says distribution in blue. Here are my distributions. And we are going to be using normal CDF. So we are typing in here normal CDF. Now, the lower bound in this case is the negative 0.69. The upper bound is positive infinity. Now, here's the thing. Our calculator doesn't understand positive infinity, but what I'm going to do is I'm going to put in just a really, really, really big number. You don't need to ask anybody how many nines, just a bunch. So, and because it's standard normal, meaning the mean is 0, standard deviation is 1, we don't need to put in the mean and the standard deviation. When that changes, then we'll have to adapt. So I'm going to type in negative 0.69, comma, 999999999 Now, your interface with your TI-84 may look different than this. So it probably will say, it'll have the top line will say lower. You'll put the negative 0.69. The next line will say upper, and then you put in the 99999 and make sure the mean is 0 and the standard deviation is 1. And then just hit go. I think it says paste. And there we are. So the area under the curve here is about 0.7549. Now, I want to point out that that is more than 50%. In fact, if I were to cut this straight down through 0, the area to the right of that is exactly 0.5, 50%. So it stands to reason that if I'm to the left of it, I'm going greater than, that I'm going to have more than 50%. All right, let's try more. Find the area under the standard normal distribution curve to the right of 2.33. All right, let's draw that out. That's terrible. Let's try it again. This is Z, this is 0. 2.33 is to the right. It's over here, way over here actually. 2.33. We can see this area here is not very much. So I'm going to guess not only is this less than 50%, this is going to be way less than 50% is my guess. So here we go. Normal CDF, the lower bound in this case is 2.33. The upper again is a big number. And I don't need the mean and standard deviation. If you have an 84 with a different interface, it should say 0 and 1. So here we go. Second, vars, and above the vars it says distribution. Normal CDF. 2.33, comma, big number. And as I guessed, it's definitely something less than 50%, way less. All right. Now we're going to go the other way. We're going to be using this time inverse norm, and it's only going to be the area to the left. So if it's area to the right, we're going to have to trick it a little bit. All right, find the z value. So now we're going to be given the area. We're looking for the z value on the z-axis itself. So this is the z-axis. Find the z value that corresponds to the given area in the figure below. Use a graphing calculator and round the answer to 4 decimal places. Okay, so area to the left, I don't know what that is right now, but I'm going to do this. I'm going to use inverse norm. The area to the left, because they're shading the area to the right, I'm going to actually do 1 minus what they give me. So I'm doing the complement. Now, we don't need to put the mean and standard deviation unless it's something other than 0 and 1. So here we go. I'm going to hit second vars. And my third one down is my inverse norm. And I'm going to do 1 minus 0.9911. Now, before I hit enter, I want to notice this is going to be way more. Notice it's already more than 50%. And notice my z value is definitely going to be to the left of 0. So I expect my z value in this case to be negative. And it is. Negative 2.36975. It doesn't say where to round. Oh, it says round to 4 decimal places, so that's fine. Let's make that into 8. Oops. Is that 8? Yeah. There we are. All right. In the standard normal distribution, find the z value that corresponds to a 79th percentile. Ooh, there we are with the percentiles again. you most likely have forgotten most of what you learned about percentiles, so let's refresh our memories a little bit. So this, again, is Z. Here is 0. The 79th percentile, if you remember, 79th percentile is the location where 75% of the data is below it. 79. Now notice it's area to the right, so that's good. So when we use inverse norm, we don't have to do the complement. Second, distributions, inverse norm, 0.79. And I'm going to guess my Z value is going to be positive because it's to the right of 0. That was right. So my Z value in this case, is about 0.8064. Now you might think that that's area under a curve, or probably it's not. It's a distance from 0 is what that is. Let's see. 0.8064 is the value on the Z-axis, is what that is. All right, we are now going to talk about critical value. This is something that is not that important yet, but becomes important. And we use inverse norm. It's always going to be 1 minus the alpha, the subscript, whatever that is, the 0.01 for the first one, 0.025, second one, and 0.05 for the third one. And we're always going to use 1 minus because that area that they're talking about is always the area to the right, which means we need the area to the left. So it's going to be 1 minus. So Z sub 0.01 is going to be inverse norm of 1 minus 0.01. Let's see what that is. Inverse norm, 1 minus 0.01. So about 2.3263. We don't know what to do with these numbers yet, but we will eventually need these numbers. Let's do Z sub 0.025. Let's see what we get. Second, distributions, inverse norm, 1 minus 0.025. I typed that in incorrectly. Let's do that again. Second inverse norm, 1 minus 0.025. This is about 1.9600. And for the last one, we're going to get inverse norm, minus 0.05. Let's see what we get. Second, distributions, inverse norm of 1 minus 0.05. It's about 1.6449. And that is section 6.1. I hope you found it helpful.